Let's talk about right triangle trigonometry. So first of all, in a right triangle, it's a right triangle because it does have a right angle. Right angles are denoted in pictorial representations by having a square in the corner, meaning that this is the 90-degree angle. Okay, if you want to talk about angle A here, from angle A across from it is the opposite side. From angle A, the side next to it is called the adjacent side. The side opposite the largest angle on a right triangle, the 90-degree, the right angle is the largest angle, and the side opposite the largest angle is called the hypotenuse. So here, for example, we can talk about just reiterating the idea of this triangle. If you have a point XY, let's say your angle is pi over 3 or 60 degrees. The equation of the outside perimeter, the equation of the circle here is x squared plus y squared equals 1 because the circle is centered here at the origin. If I want to think about taking my point and dropping a line down to the x-axis, if I drop a line down, I have now created a perpendicular line to my x-axis. Perpendicular lines meet at a 90-degree angle, which is what we have drawn over here. We've dropped a line down. We've made a 90-degree angle. We know that this angle right here is pi over 3 or 60. If this is 60 and this is 90, we can already understand the idea of the value for this angle simply doing subtraction. Remember, the angles in a triangle have to equal or add up to 180 degrees. So if you have the 180 degrees, and you already know that one of them is 90 and one of them is 30, that must make the other one, this angle here, this angle here must be 60. Oh, whoops, I'm sorry. This one's 60, this one's 30. Sorry about that. So let's talk about this. If I drop a line from my point to the x-axis, this is a distance of y. If I draw that line from my origin to the outside of the circle, again, the unit circle has a radius of 1, therefore this distance is 1. If I go from my origin out to my dropped line, this is distance x. Now the reason we've generalized it as y and x is because I don't have any tick marks or anything on my circle here. So let's talk about how we can construct a right angle. We talked about that by dropping a line segment perpendicular to the x-axis. So now we can view pi over 6 or 60 degrees as the measure of the acute angle in the right triangle. Now, sine of pi over 3, sine of 60. You remember sine for a unit circle is y. So if I come back to my picture here, I need to basically have this answer come out to be y. Well, the way to do that is to have that be the length of the opposite side, from this angle, the length of the opposite side, y, divided by the length of the hypotenuse. For a unit circle, that's 1. Y over 1, that's y. For cosine of pi over 3, cosine of 60 degrees, I need to have this to come out to be x, and the only way to do that is to have it to be the length of the adjacent side, x, over the length of the hypotenuse. Again, for a unit circle, that's 1. X over r, x over 1 will give you x. There is a statement on how to remember this. It's SOHCAHTOA. I prefer a different method. I like rhymes and limericks to remember things. So for example, we have an S, an O, and H. Some old horse. C, an A, and H. Caught another horse. T-O-A. Taking oats away. So we have some old horse caught another horse, taking oats away. Sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. That takes us to the Pythagorean theorem. Pythagorean theorem is a squared over b squared equals c squared. The sides squared is equal to the hypotenuse squared for a right triangle. Again, this is just talking about, well, if I understand my SOHCAHTOA, or some old horse caught another horse taking oats away, I can come up with this. Sine of my theta, sine, hang on, my pen's not working. Sine is opposite over hypotenuse. From this angle, opposite is A, and hypotenuse is C. So I have sine of theta is A over C. If I want to talk about cosine, adjacent over hypotenuse, cosine adjacent is B, hypotenuse C, so I have cosine B over C. Tangent, opposite over adjacent, so I have tangent opposite is A, adjacent is B, so I have tangent A over B. We understand that cosecant is the reciprocal of the sine, so flip the quantity. Secant is the reciprocal of the cosine, so flip the quantity. Cotangent is the reciprocal of tangent, so flip the quantity. Now we can start working on problems using our new right triangle trig identities. First of all, I know side B is 12, I know A is 5, but I do not, however, know the value of C. But that's okay, because this is a right triangle, which means I can use the Pythagorean theorem. A squared plus B squared is C squared. Okay, so A squared, that's 5 squared. B squared, that's 12 squared, equals C squared. Well, 5 squared, that's 25. And 12 squared, that's 144, is C squared. And 144 plus 25, C squared, is 169. Now, if I want to get C by itself, I have to take the square root. You remember squaring a square root cancels this out, and so you get plus or minus the square root of 169. C is plus or minus 13. We're talking about distance here. Distance can only always be positive, therefore C is positive 13. Well, now I can find all 6 trig function values. Sine of theta is opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. Cosecant, the reciprocal of the sine. Secant, the reciprocal of cosine. Cotangent, the reciprocal of tangent. So sine, for my angle theta, opposite is A, which is 5, over hypotenuse, which is 13. Cosine for theta, adjacent is 12, hypotenuse 13. Tangent, opposite for theta is 5, adjacent is 12. For cosecant, it's the reciprocal of the sine, so it's hypotenuse 13 over opposite, which is 5. Notice that this quantity is the reciprocal or flip of the sine value. Secant is the reciprocal of cosine. It's the hypotenuse, 13, over the adjacent, 12. Again, notice that this value is the reciprocal or flip of the cosine. Cotangent is the reciprocal of tangent, so it's the adjacent over the opposite. And notice that this value is the reciprocal or flip of the tangent. Okay, let's do another one. Here again, using our Pythagorean identities and Pythagorean theorem for a right triangle, because again we're talking about a right triangle. We again want to find the value of the 6 trig functions. In order to find the 6 trig functions, I do need all 3 sides. Now because this is a right triangle, I can go ahead and figure out the side that's missing, because I'm going to use my Pythagorean identity saying that the sides squared is equal to the hypotenuse squared. A squared, that's 1 squared. B squared, I don't know it. C squared, that's 3 squared. Well, 1 squared, that's 1. B squared. 3 squared, that's 9. Solve for b squared. Now I want b by itself, so I'm going to take the square root of the b squared to have the square root and the square cancel. Now let's talk about the square root of 8, because if you write b equals plus or minus the square root of 8, that's incorrect, because it's not so-called simplest form. I mean, they are exactly equal to what we're going to come up with, yes. But in problems in your MyLabs Plus, and your exams and things like that, what we have to do is we actually have to break this radical, because it does break. If a radical breaks, breaking it makes its simplest form. Okay, so let's talk about this. 8 factors of 8 is 2 and 4. 2 is prime and can't be broken, but 4 can. 4 can be broken into 2 and 2. This is called a factor tree. And any time you want to break a radical, you have to do what we call a factor tree. You basically break the number into its primes. 2, 2, 2. The ends of the branches are primes. Okay, now, we understand that a square root has a little index number that we never write, but it's implied here. It's implied that this index is 2 for a square root. For a square root, that means I need 2 things that match in order to pull it out of the root once. Again, I need 2 things that match in order to pull it out of the radical once. I have 2 2's here. Those match. I pull it out once. What's left? 1 2 by itself. So that the square root of 8 is 2 square roots of 2. When you break a number, you never talk about those numbers again. You talk about the ends of the tree, okay, the ends of the branches, the primes. Again, we always take the positive because we are talking about a distance here. That means that the distance of b is 2 square roots of 2. Okay, let's go find our 6 trig functions using our new sides. Sine is opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. Cosecant is the reciprocal of the sine. Secant is the reciprocal of cosine. And cotangent is the reciprocal of tangent. So sine, here again, is our angle theta. Sine is opposite, so that's 1 over hypotenuse 3. Cosine, adjacent, that's 2 square roots of 2 over hypotenuse 3. Tangent, opposite, so that's 1 over adjacent, 2 square roots of 2. You cannot have a radical in the denominator, so we have to rationalize. So we get the square root of 2 over 4. Now you might be going, hey, wait a minute, how'd that 4 get there? You remember that if you take the square root of 2 times the square root of 2, if I take the square root of 2 times the square root of 2, that's like saying the square root of 2 squared. And what happens? The square and the squared, they go away, so you're just left with the number 2. So that these 2 pieces together give you a 2, and a 2 times 2 is a 4. Cosecant is the reciprocal of sine. So we have the hypotenuse, 3 over the opposite 1, which would just give you 3. Secant is the opposite of cosine. So we have hypotenuse 3 over adjacent 2 square roots of 2. Again, we cannot have a radical in the denominator, so we do rationalize. So on top we have 3 square roots of 2 on top. Let me write that a little better. We have 3 square roots of 2 on, on top. And then here we have the square root of 2 and the square root of 2. That gives you a 2, and a 2 times 2 gives you a 4. Lastly, cotangent is the reciprocal of the tangent. So we're going to get adjacent, which is 2 square roots of 2 over the opposite. 2 square roots of 2 over the opposite, which is 1, or just 2 square roots of 2. Okay. One thing to realize is that, yes, these functions are reciprocals of each other. For example, the tangent value, the end result, was square root of 2 over 4. But before we did that, we had this value, 1 over square root of 2. That value had to be rationalized to get our end result. Now the cotangent is the reciprocal of the tangent. And if I flip this identity, 2 square roots of 2 over 1, that's what I'm getting here. So yes, we are getting the idea of the reciprocals, but the end results may look different, based on if you have to rationalize or not.